Well, I'll talk about the spatial regression analysis to analyze factors affecting electricity usage in residential buildings in Seoul City, focusing on environment influencing factors during heat wave period. And I'm the first author of this research. My name is Hyun Kim, and the presentation's table of contents as follows. First of all, there will be introduction, literature review, analysis results, conclusion, and limitations as follows. First of all, talking about the introduction of this study, we can see that in cities, building energy consumption accounts for more than 70% of global GHG emissions. In Seoul City alone, it accounts for about 68%. As such, energy consumption from the building sector in cities has a significant impact on the final energy consumption of cities, especially in the period where summer electricity demand is increasing due to global warming. An in-depth analysis of the influencing factors of summer electricity consumption is a priority for efficient management of GHG emissions that will increase in the future. And we can see that for the building sector, electricity consumption is 46% in Korea's final energy consumption in 2020. Moving on to status of direct GHG emissions by 17 metropolitan local governments and sectors in 2019, we can see that GHG emissions from the building sector in Seoul City alone accounted for about 10.6%, which is the highest among 17 municipalities in Korea. In Seoul City alone, with the goal of converting 1 million buildings to low carbon buildings, Seoul City promoted zero energy building conversion for public and private buildings. In the 2021 Comprehensive Plan for Climate Change Response, Seoul City aimed to reduce the use of fossil fuels, which takes up to 67% of energy consumption in Seoul City, and various new renewable energies such as hydrothermal, geothermal, and fuel cells. In addition to the conversion of the zero energy building and building retrofit project, Seoul is promoting the total building energy consumption system project. Moving on to the scope of study, for the study, the electricity consumption data for residential buildings in Seoul City was provided by the Ministry of Land, Infrastructure and Transport, and the monthly electricity power consumption of buildings in July of 2021 was collected and categorized into 426 districts in Seoul, and the temporal scope was set to the tropical night period of July or August 2021, which is the hottest period observed in Korea. Because the data for electricity power consumption in single-family houses was unavailable, the analysis focused on apartments, townhouses, multi-household housing, and multi-unit houses, which also include houses in non-residential buildings. And the research methods of this study, we can see that it focused on three different measures, which is first, the spatial autocorrelation to identify whether the spatial dependence existed in the data. Second, the OLS regression analysis. Third, spatial regression analysis to verify whether it's happening. And it's a method that can analyze the spatial dependence caused by the interaction between the spatial units by reflecting it in a regression model, and generally uses a spatial lag model and a spatial error model. Also, we used ArcGIS, Moran's-I index, as well as LISA and hotspot analysis, and Python with Python spatial analysis library to verify whether our study and the hypothesis that we made for the study was right. Moving on to the literature view of this study, in previous literature, there were the building structure, age, density, area, the building year of the house representing the energy efficiency of the building, and the type of house and the size of the house were also considered. However, only the temperature in July in the summer, which is the temporal range of our study, was reflected. And for socioeconomic factors, there were demographic and household characteristics and single-person households considered for previous literature. And in addition to such previous literature, we also included the per capita ratio of single-person households, living population, and the number of people per household, and the number of old houses, and the average price per unit of the districts that were calculated. Moving on to the third category, which is urban spatial factors, we saw that in the previous literature, there were building factors such as roof, building structure, building type, and size affecting energy consumption. And in apartment buildings, the larger the total floor area, the higher the energy consumption per unit area, analyzed by limiting it to 50 meters. I found that future research should explain the surrounding environment of a building and the building energy influencing factors by housing type that's necessary for future research. Moving on to the variable setting, which is part of the analysis results, we found that the variable for analysis is the energy consumption of multifamily housing used as the dependent variable, as stated in previous studies. And among the independent variables, explanatory variables, environmental and physical factors were set as year of construction, building area, and surface temperature, and socioeconomic factors were set as per capita ratio, living population, or the number of people per household size, number of old housing units, as well as housing price. And for urban spatial characteristics, we can see surface area by each district, population density, and green space ratio. The spatial autocorrelation analysis of electricity energy consumption in apartment buildings by each district in Seoul City shows that spatial autocorrelation exists with a Moran's I index of 0.12, as shown in the table here. And the spatial autocorrelation means that the observations in a particular region are correlated with observations in the neighboring regions, leading to potential errors in observations. So it's necessary to apply a model that considers spatial autocorrelation other than the traditional model. And before analyzing the spatial regression model, this study first verified the spatial autocorrelation of electricity usage consumption with environmental, physical, socioeconomic, and urban spatial factors by utilizing a spatial statistical model that can control the correlation of electricity usage in apartment buildings. First, we used LISA to examine the spatial distribution of electricity energy in Seoul City. It's a spatial analysis method that compares a specific area and its surrounding areas to find areas that are different from its neighbors. It provides a cluster map that shows the degree of spatial autocorrelation and categorizes the types of spatial auto-association into 4 types: high, HH, as you can see here. When regions with high index values are near each other, LL, when low values are near each other, HL, when high values are near low values, and LH, when high values are near the low values. The areas classified as HH in the results are areas with high spatial correlation in electricity energy usage, which can be considered as areas where electricity energy usage of apartment buildings is densely concentrated. So as a result, the hotspot analysis shows that electricity usage is concentrated in Gangnam-gu and Seocho-gu area, including Nonhyun 1 and 2 dong, Yeoksam 1 and 2 dong, Yangjae 2 dong, Samsung 2 dong, and Pangbae 3 dong. So therefore, Moran's I and Lee's analysis shows that there is a weak spatial autocorrelation as a result. This study empirically analyzes the factors affecting electricity usage in apartment buildings using a spatially weighted regression model. To achieve this, we first examined the variation of the results by introducing first environmental physical factors, socioeconomic factors, and urban spatial factors, which are considered to be have a universal influence on electricity energy consumption in each district of Seoul City. And the monthly electricity consumption was set at the dependent variable, and the data for the variables that affect such consumption was set at the dependent variable, was built, and it was built using Python method, and the linear regression model and the spatially weighted regression model are estimated and compared after pre-processing. As you can see in the equation in the right-hand corner, in the spatial regression analysis model, y is the dependent variable, and p, small letter p, is the spatial autoregressive coefficient. So the spatial autoregressive coefficient p represents the effect of neighborhood on the value of dependent variable. WY is derived by multiplying the spatial weight matrix W by the dependent variable Y, which represents the spatial relationship between observations. And furthermore, x1 to x10 show the independent variable matrix, and beta 1 to beta 10 show the respective regression coefficients that estimate the association between the independent and dependent variables. Finally, the error term represents the residuals and captures the unexplained variability of dependent variable with zero mean. And so according to the linear regression analysis, moving on to the previous slide, sorry, the statistical significant variables affecting such consumption on a variable by variable basis are the number of old houses, the area by each district, the number of people per household, the area of construction, and the green area. Similarly, the variables with high correlations are the number of old houses, area by each district, and population per household, while the construction year and green area have relatively low values of correlation. In contrast, we can see that the variables that showed the opposite characteristics were the per capita ratio, population density, and surface temperature, which were negatively correlated with electricity usage in apartment buildings. To be more specific, the regression coefficient of the per capita ratio was approximately negative 153. The population density was negative 47, and the surface temperature was negative 42. Detailed analysis shows that the number of old houses was about 6 times more correlated with the per capita ratio. In addition, we compared the results of the linear regression and spatial estimation. For example, in the case of per capita ratio, the OLS model showed a positive effect, which shows that it's a significant variable, while the spatial model showed a negative effect, showing that's negatively correlated. In other words, it means that the per capita ratio variable has different impact in different regions, and in certain regions, it shows negative impact on dependent variable, which is electricity usage. As a conclusion, we can see that the spatial regression analysis shows that the factors that are specifically significant are the number of houses, old houses, the total area of each district, and the per capita ratio. Secondly, the distribution of electricity consumption in old buildings in Seoul shows that top 10 districts are mainly located in the southeast and along the Han River. The study also provides implications for designing energy reduction pathways to reduce GHG emissions and budgeting by each district in Seoul. And this will in turn support the implementation of energy efficiency projects and enhance the effectiveness of policies related to Seoul's energy efficiency performance. As limitations of our study, there was data limitation because data of single-family houses and apartments with less than 300 units was unavailable. Secondly, the temporal scope was only limited to the electricity usage in July, and if there were to be the entire seasonal scope to be considered for future empirical analysis, it would be there will be further study possible. Thirdly, there should be more improvement in statistical model and explanatory power of variables, as a more meaningful energy consumption indicator such as building use or energy usage per unit area should be added for further study. And this is the end of my presentation. And these are the references that I referred to while I was doing the study for our research. Thank you so much for listening.